This week, we introduced multiple regression. Last week, we focused on bivariate linear regression. And so today we're going to move to talking about multiple regression. And today's lecture covers the first 3 chapters of the Allison book, Multiple Regression, a Primer. So last week we introduced bivariate regression and we practiced calculating linear bivariate regression with several different examples. This week we start talking about multiple regression, and we can think of that as bivariate regression on steroids. It's often not enough to look at how a single independent variable connects to or influences a single dependent variable. We talked last week about how that model is really simple, and that in reality, many factors can influence the outcome of a dependent variable. For example, if we want to talk about income as our dependent variable, there are several factors that influence how much money someone makes. Things like gender, race, education, occupation, years of employment. All of these things influence someone's income. Linear bivariate regression only takes one independent variable into account, but multiple regression or multivariate regression allows us to look at the individual independent impacts of multiple independent variables on our dependent variable. Mathematically, it does this by measuring the individual impact of each independent variable while holding all of the other variables constant. In Chapter 1, Allison points out that there are 2 major uses of multiple regression: prediction and causal analysis. For prediction, the goal is to develop a formula for making predictions about the dependent variable based on the observed values of the independent variable. In causal analysis, the independent variables are regarded as causes of the dependent variable. The aim then is to determine whether a particular independent variable really affects the dependent variable and to estimate the magnitude of that effect. Last week, we not only calculated regression, but we also calculated R-squared, which told us about the predictive value of our independent variable and the percentage resolved or explained, and how often we could predict the dependent variable correctly by knowing the independent variable. And multiple regression will do the same thing. Later, using SPSS, we will calculate what we call partial slopes. We talked about slope values last week, and we're going to call them partial slopes when we talk about multiple regression. We're going to do that for each independent variable, and we can calculate R-squared or partial coefficients for each independent variable to determine how much each variable explains of the dependent variable. Regression is referred to by several different names: ordinary least squares, linear regression, least squares regression, OLS regression, multiple regression, and multivariate regression. In addition, there are other types of regression that we will introduce in the last week of class. These additional measures are used when we have violated some of the assumptions that are required for OLS or linear regression. And this will make a lot more sense later. As with bivariate regression, we talked last week, multiple regression is based on an assumption of linearity, an assumption of a linear equation, a linear relationship between variables. In other words, there's a straight line through our data, and the data itself is not curvilinear. We'll come back to some of the other equations and some of the other assumptions about linear regression and multiple regression, but the notion of linearity is key. We can use a number of different techniques to determine linearity, such as plotting our data on a scatter plot. But we do have ways of addressing nonlinear relationships using some of the modified or alternative forms of regression that, as I mentioned, we'll talk about the last week of class. So this chart on the left here is a linear curve looking at the impact of schooling on income. So we see this nice straight line relationship. On the right, we have a curvilinear relationship that looks at the effect of age on income. So notice that this kind of goes up and then down, and we can expect that that might be what happens with this curve. So the income likely increases until we hit middle age, and maybe 55, this is about the point that it's the highest, and then it starts to decline again. And what happens at that point? Well, that's when most people are going to be retiring. So it would increase up until retirement age, and then income would decrease again after that. So this is a non-linear relationship. It is a curvilinear relationship. And we make an assumption that the relationship is linear when we're running regression, but not all relationships are linear, and we'll have to use a variation of linear regression in order to address these curvilinear relationships. But Allison does point out in the book that we can use linear regression to provide an estimate of the relationship, even if the relationship is curvilinear in nature. We looked last week at the basic equation for linear regression when we had two variables, when we had one independent variable and one dependent variable. And that's what we see here at the top of the screen. What does an equation look like when there is more than one independent variable? In this case, we expand the equation to include additional independent variables and then label them with subscripts to differentiate them between the different independent variables. This is similar to the way that we labeled multiple groups and their means when we calculated two sample t-tests and ANOVA. In order to perform regression analysis for multiple independent variables, the process is very similar to what we did for linear bivariate regression, although it's more intricate because we have to take multiple variables into account. I'm not going to talk too much this week about the process of calculation because I really want to focus on the logic of multiple regression and understanding regression output before we get down to the dirty work of calculation. You'll also be happy to know that I have no intention of making you calculate by hand any multiple regression analysis. We will let SPSS take care of that for us. What's most important, though, is that we understand what the process looks like, the logic behind that process, and then how we interpret the SPSS output. Allison uses the example of looking at age and schooling simultaneously as predictors of income. And in that case, you can see that there is additional complexity to adding variables. In fact, he describes the resulting graph that you would get as three-dimensional rather than two-dimensional because there are multiple slopes, one for each independent variable in trying to graph the equation. So you would have the slope for your first independent variable, maybe age, and then you would have the slope for your second independent variable, schooling, and that would end up, in our case, presenting a three-dimensional mapping of the line, or result, what he would argue would result in a plane going through that three-dimensional graph. And it's okay that that doesn't quite make sense, as long as we understand what our resulting slope coefficients mean for each individual variable that we are factoring. In theory, linear multiple regression is based on an assumption that we are dealing with quantitative data. That means we're dealing with numeric data, where the numbers stand for numbers. We know that this isn't always the case, that we don't always have interval or ratio level data to work with. And as Allison points out, quote, strictly speaking, ordinal variables are inappropriate for multiple regression because the linear equation to be meaningful requires information on the magnitude of changes, end quote. But in reality, ordinal variables are used pretty often. But as we did previously in the semester when we were looking at things like central tendency, we have to be very careful about the interpretation. So we have to make sure that we go back and understand that we're dealing with a non-quantitative measure when we make the interpretation. If you recall measuring range on ordinal level variables, the response that SPSS gave us didn't really make sense because it gave us a numerical output for the range, even though, and for the median, even though those numbers didn't really make sense. When interpreting regression output, we're saying that an increase or decrease in a particular value of a unit of the independent variable has a result on the dependent variable. But if this unit isn't actually a numerical unit, it's a label like you would have for an ordinal level variable, the interpretation is less straightforward. So we'll come back and talk about those interpretations, but we do often violate this assumption. In fact, what about nominal level variables? The short answer is yes, we can use nominal level variables when we're dealing with multiple regression, and we have independent variables that are measured at the nominal level. To do this, we create what we call dummy variables, where we simply assign a value of 1 or 0, and then make comparisons of two groups at a time from that nominal variable. So think about biological sex as an example, male or female. We could set up our dummy variable to be female equals 1 and male equals 0, and use that to represent the female yes or no kind of category. We would need to be careful in our interpretation because after we run our analysis, our slope is going to say a unit change in gender brings about so much of a change in the dependent variable. And this doesn't make any sense. So we're not trying to say that as you move from male to female, a unit change in male to female. What we're really saying is that females score blank units higher on this dependent variable or something like that. We'll come back and talk about it more when we have an example. But we have to remember when we're doing our interpretation that the number doesn't mean a number at all, that it's actually referring to a nominal level categorization.